Good morning and welcome everybody. Thanks for coming by. Today we're going to be talking about a new course that Eric Zimmerman and I have just completed writing, Forensics 498, Battlefield Forensics and Data Acquisition. We're going to be going through the course a little bit just to give an idea of what is involved in the course and some of the things that you're going to learn so that if anybody's considering taking the class, they'll have a better idea of what is involved. A little bit about me on the screen. I own a company. I do some different things, and you can go back to this later and look at it if that's what you're interested in. But we've got more important things to talk about than me, specifically this course. Now, this course, as I said, was written by myself and Eric Zimmerman. There's two basic sections to the class. Half the class is, or a little more than half the class, is focused on battlefield forensics, and the remainder of the class is focused on data acquisition. And then there's some esoteric stuff thrown in at the end, just it's not really things that would fall into the battlefield forensics category, but it's a little bit of deeper diving stuff that we've seen people struggle with in the past or have many questions about that we just decided to address in the class. We're hoping that very shortly we'll have a spot on this slide with our course and our coin. So the kind of the idea of where this came from was, first of all, when it came to the data acquisition portion, we noticed that certainly with the Forensics 500 and in some cases Forensics 508, the students were showing up and they were saying, you know, it's great that we're working with this forensic image, this E01, but how do we get that? Where does that come from? And you know, back in the day, where, you know, we're going back quite a number of years now, you would get a significant amount of people, typically law enforcement, coming to the forensics classes who were already in the forensic space and for some time, and were looking to hone their skills and look for alternative ways to affect evidence. So when they would show up in class and they would be being taught acquisition in the forensics classes, the general feedback was, you know, we already know how to image a drive, so why are we wasting time in the class with this? So it was subsequently dropped from the class and replaced with more and deeper information. But fast forward to today, where a significant amount of attendees now in the forensics classes are people who have never done forensics before or are very new to forensics, and they don't have the background and they don't know, you know, how do we get that E01? As well, a lot of things have changed over the years. Besides, you know, we'll say back when dinosaurs roamed the internet, when you wanted to image a drive, you pulled it out of the computer, you hooked it up to a write blocker, and you imaged it, and then you forensicated it. Nowadays, we see so many different types of devices that it just doesn't work that easily. We have Surface Pros where you have one port to access the whole piece of equipment, and the Surface Pro can't be taken, well, it can be taken apart, but you're not going to have much to put back together. A lot of Apple devices, things like that, non-standard. So we'll talk about acquisition of those. Then the battlefield forensics portion was basically styled around the notion that data sets are getting huge and we need to find better ways to address them. And we'll talk more about what fits into that category shortly. The course is broken down 6 days like a standard SANS class. Day one is evidence file quick wins and dealing with smartphones. We talk about data and how data lives and moves, how it sits on a drive, how it's created. We get into file systems and talk about different evidence file types. And then we look at quick wins as far as smartphones are concerned. Very few cases today are not affected by cell phones. And, you know, there's a lot of questions surrounding them. A lot of people talk about smartphones, but when it comes right down to grabbing data, what can they do with it? Then day two, or section two, goes into evidence acquisition and collection. We talk about things like scene management. How do you control the scene? What happens at seizure? And this is not just from a law enforcement perspective, but certainly any perspective, because especially in the forensics field, we have to approach every single job as though we are handling evidence, because we potentially are. You can never know at the beginning of a case whether it may someday end up in court. And if you end up in court, you can't go back and unbake that cake. You can't go back and recollect the evidence properly. So it has to be done from the beginning properly. And we often see many mistakes being made with collection. Then we talk about data acquisition, how that's done. Section 3 gets into the quick wins forensics. How do we get at stuff quickly and make it make sense for us when time is of the essence? So we talk about different methods for mounting evidence. We get into why some ways are better than other ways. What are the advantages and disadvantages of some of the commonly used tools that we see? We get into triage of data. How do we collect data? Because we realize that the data that we use for evidence is a small portion of the actual size of the drive. So what do we want quickly, and how can we get that quickly? We talk about RAM. We don't get into RAM analysis, but we do talk about why we want the RAM, why it's so critically important, and how to collect it. Then we talk about live acquisition, how to acquire data from systems that are running when we arrive. Then in section 4, non-traditional and cloud acquisition, we talk about the battlefield forensics and specifically and how we can get at the data very quickly. Remote acquisitions, what happens if the computer's not physically in front of you, but it's within the network or even in a remote network? What are the abilities available to us? We get into multi-drive storage, things like working with RAID or working with huge storage arrays, and some of the considerations that you have to have when you're extracting data from there. Then we talk about network acquisition, and this is getting more towards things like online repositories, Dropbox, Gmail, things like places offsite where most any user today has a presence. Then in section 5, we get into Apple acquisition. Now, again, we don't talk about Apple forensics here, but we do get into Apple acquisition. There's a number of different things we have to consider with Apple products, and not a lot of people are talking about that. Internet of Things is becoming pervasive. Cameras, front door cameras, thermostats, garage door openers, basically anything that connects to the internet, toasters, fridges. And then online attribution, how do we tie stuff to people? How do we get a blog post or an email or something like that back to a person? And then in the final section, we get away from both battlefield forensics and data acquisition and get into things like data carving, where all of the quick win stuff hasn't gotten what you would have expected, or you just need to, the pressure's off and now you need to deep dive. So we'll talk a little bit about data carving and rebuilding. And then we have a section on data recovery, and we'll show a little bit more on that as we go along. Now with battlefield forensics, the big push behind this was the fact that there is so much data today. And even simply on a machine, in many cases, you have hard drives that are 1 terabyte, 2 terabytes, 4 terabytes in size. And so the way that we used to do this is becoming untenable. The amount of time it takes to acquire large drives or even standard drives of today significantly impacts the amount of time it takes to get at the data that you need. If you look at a situation like the Las Vegas shooter or something like that, where there's a pile of tech laying around, and they need answers immediately. They don't have time to be imaging things and parsing them and indexing them and mounting them and then looking through them. We need a way to get at that data. And so that's where this class has come from. When we say going from seizure to actionable intelligence in 90 minutes or less, I know that sounds like a bold claim to the traditional forensicator, but we're doing it. And in fact, I'm going to be showing you a tool that Eric Zimmerman wrote, among many that he's written, that has actually maybe even affected that timeline, because you'll see that when we do a demonstration of collecting things with CAPE, we don't even have time to go for a coffee before our data is ready to look at. Now, we know that today, well, we've known for some time that 98% of the data that we use in investigations is in 1 to 2% of the storage space on a hard drive. And so we need to change our approach so that we're going after the data that we need right now. Now, that doesn't mean that we're not going to be imaging drives. It just means that maybe we're not going to image them immediately. Maybe we're going to do some triage or some triage acquisition to pull out that 1 or 2% of the data, so that we have 98% of what we need, so that we can at least get the ball moving on our investigation while the imaging process is happening. Now, before even that happens, there's areas where we often see a lack of collection or information, things like the system BIOS, UEFI, collecting the RAM, as well as logs, router logs, switch logs, firewall logs that people aren't collecting that become important later. And it is very, very difficult to answer to why you did not collect this at the time, because in the case of RAM, you having to explain to a court or somebody, even your boss, why you potentially threw away 8 gigabytes or 16 gigabytes of data that doesn't exist anywhere else. And that's a pretty tough question to explain, especially if you've got a forensicator on the other side of the matter who can very clearly and vividly explain what it is that you threw away. So then we look at, where does the data live? We look at a number of different devices. And by the way, through this presentation, I'm hitting highlights. There's so much more in the class that we don't even have a chance to touch on in the limited time that we have here. But we do get into where data lives, and we get away from, the traditional stuff into, network storage, removable storage, cloud storage, unorthodox storage, which we'll talk about in a little bit. And we address the difficulties with showing up on site and connecting to devices. So we have a section on interfaces, and we talk about fairly common interfaces that we come across today. And we talk about adapters and adaptability of certain things. And, we talk about how to put together kits for ensuring that when you show up on site, you have the tools that are helpful to you. And again, we talk about the importance of the BIOS and the UEFI at the time of collection. You only have one opportunity to collect this, and that's at the time of collection of the device. We have seen cases, many cases in our lab, where this information isn't collected at all. And there's a number of legal reasons why this is incredibly important to us. As well, when we go to look at this stuff, we see cases where once we question it, then the people on the other side now pull out the hardware and grab the BIOS information. But 6 months after the initial collection, this is unacceptable, because we don't know what's happened with that equipment in 6 months. Quite frankly, in 6 months, the CMOS battery could have died, and now the BIOS information is no longer accurate. So we talk about the importance of both the BIOS and the UEFI, why we use it, and how to capture the information. One of the really cool demonstrations that we do, and we also have a lab on it in our class, is booting an E01 file. And some of you might say, are you kidding me? How do you do that? It's a flat evidence file. How can we do anything with it? Well, we can, and there's a number of different ways to do it. There have been commercial tools that have done it to limited degrees of success for some time. The way that we demonstrate is, I wouldn't say free, but certainly with the software that you already have, it's possible. And the reason why it's so important, especially today, is because we can see things in a booted environment that we can't see on an E01 file. With an E01 file, we get a flat file. We get to mount that, and we can look at it as though it were an external drive connected to our systems. But what we don't get to see is what the user saw when they interacted with the computer. What's on the desktop in terms of things that you can't access. For example, the notes, the sticky notes that you can put on your desktop. In Windows 10, there is not a viable way to pull the database that holds those notes currently. We used to be able to do it in Windows 7 and I believe Windows 8, but after that, the structure that the notes took on, you can get at the file, but there's nothing to parse it with. So that, for example, and I'm going to show you a demonstration where we'll go through why something like that might be important. So we're going to have a look at this and see if we can get this to work for us. Now, you get in the class, you get two VMs. One is a Linux VM and one is a Windows VM. And so in the Linux VM is where we mount an evidence file. So we're going to do that right now just so you can get a sense of what that looks like. Now what I've done is I've grabbed some code here already just so I don't have to type it. I'm not as fast a typer as many, so it's easier for me to just cut and paste. So basically what we're doing is we're pointing the tool at a VM that, or at a E01 that we've already created. And we're going to convert it to a VMDK. Now, one of the things that has happened in the past is that a lot of the tools require you to convert that E01 to something like a DD or a raw file before they can interact with it and mount it, which obviously takes hours and hours and hours and hours, if not more, depending on the size of the evidence file. Well, we have converted that already, and we're going to do more conversion on the fly, so you get to see just how quick that actually happened. So after we did that, now what we want to do is we want to look and see, did it actually create properly? So we're going to go over and we're going to have a look at where we wanted it to output, and we do in fact see that our Windows 10 VMDK was successfully created. So once that's been created, we can open up VMware Player is what we're going to use in the demonstration here. And we're going to create a new virtual machine and point it at the VMDK we just created. We want to name it or call it, point it at whatever template we need for the operating system we're going to use. In this case, it's Windows 10 64-bit. And then we've got to point it at where our VMDK is sitting.
Hey, Kevin.
Yes.
A question came in. It says, can Xmount convert to VHDX?
I can't answer that.
Okay. We'll move on then.
I'm sorry, I could make something up, but I can't. I don't know the answer to that.
All right, thanks.
So we want to point at where we put our VMDK. And we're just making various selections. I'm not going to get too deep in the weeds over this, but we do in the class go through this, and then, like you say, we have an entire lab that we do this for. And then we need to change a few settings because we've got to point it at the VMDK that we created. So the first thing we're going to do is we're going to ditch the hard drive that's in there, and we're going to create a new one. And then we need to point it at our VMDK. And I have to caution that, of course, we're doing a live demo, and we never quite know how things are going to turn out necessarily. So we have our hard disk. We're going to save that. Now, before we fire this up, we have to do one more thing. We have to change one of the files that we're working on. So I'm going to cd here into a different directory. And then I have to edit a file in here, the Windows 10 VMX. So I'm just going to make a quick change in here so that it'll boot. And we'll save that out. And now, if everything worked out all right, we should have a VM that's getting ready to boot. And in fact, it does look like it's happening. Once we see the Windows logo, we know that, in fact, our E01 is starting to boot. Excuse me. Now, when this is happening, it takes a little longer than normal. Remember, we're running a VM created from an E01 inside another VM. So we're nesting VMs. All of this, each VM takes its own amount of RAM from the host system itself. Not to mention, we have two different layers sharing the graphics card resources from the host. So things take a little longer than normal, but when you're already seeing the results, you're already seeing that chances are this is going to work. And so we're already off to the races in far less time than it's going to take for you to convert an E01 to a DD or a RAW file or something along those lines. So we see a Windows interface. So remember, we're starting a Windows VM created from an evidence file on a Linux VM, started on, in this case, a Mac that I'm running it from. So we entered the password. Now, how did I know the password? Well, you're going to have to come to the class to see how we figure that out. But we're entering the desktop now, and if everything works all right, we're going to see the computer just exactly the way that, in this case, this user Hearns would see it. So we have the computer up now. It has booted to the desktop, and we see that we have a sticky note on the desktop. This sticky note, there's no other way you're going to get this other than booting the system live. Otherwise, you may not ever know that there was a sticky note here. And you can see as I move it around that clearly I'm interacting with the system itself. Now, I'm going to do something here that obviously you wouldn't do in a forensic environment. However, just to give you an idea of the kinds of things that you would see. Now, I'm opening up the browser, and we see that the browser opens. This would take you to something like this individual's homepage, so you could see, gather intelligence from there. But I'm doing this also more for just to trigger some activity, because what I want to show you next is, you know, some of the things that you wouldn't be able to see from a dead box from just looking at an E01. So I'm just going to run, for example, so I'm going to have to change things because I was doing that from my host, and we don't want to do that. So let's go get to a command prompt here. And you can see that now we're interacting with the live system. Now, this is not affecting the evidence in any way. Nothing is changing. When we close out of this, we haven't affected our E01 at all. But we can look at things like, what is this particular computer trying to call out to. So when we do things like go to a website such as CNN.com, for example, we can see Netstat recording the callouts to the site. Of course, I'm taxing my resources to some degree, but you get the idea. You can see it establishing connections now with entities within that website, third-party redirects, various different things. So we truly do have visibility into this system, into this evidence file, in ways that most people are not used to seeing. I'm just going to set this to shut down just to free up some resources. Okay, we'll let that chew away for a little bit. So then we talk about live response. What do we do when we get to a machine that is on when we arrive? And there's a number of different approaches. Forensics 500 talks about using FTK Imager and its custom content imaging features to perform this. But this we can also collect live images with FTK Imager, with X-Waves, with various different tools. We could use F-response on the wire if we need to. And then we get to full-blown triage, where we use CAPE, and we'll talk about CAPE here shortly. Now, another thing that we talk about is various different methods of write blocking. We talk about hardware write blocking, and in fact, every student gets a hardware write blocker in the class. And but most standard write blockers write block so that you can plug the device into USB to do the acquisition. And what about non-standard or things that you can't plug in USB? For example, we did a case in the lab where we had fiber channel drives, and they were non-standard fiber channel drives with 520-bit sectors. So nothing would recognize them. We had to plug them into a PCIe adapter card, and a write blocker, a software write blocker called SafeBlock, was the only methodology we could find to write block the interface. Now, SafeBlock write blocks pretty much anything that you will connect to the system, including iSCSI connected across a network. So very, very versatile tool. They also have a product called SafeBlock to Go, which is basically a Windows to Go distro that you can put on USB with SafeBlock so that you can acquire anything that you could plug this into in a write blocked manner. And then we talk about some boot disks and ways that you can approach the system for imaging, whether it be live or dead box. How do we boot the system in a write blocked environment and write it out to a destination drive? And then we talk about image mounting. We go through a number of different variations of mounting images. Mounting an image is not the same with everything you'll look at. So probably many of you have been using FTK Imager to mount an image so that you can look through the file system. But there are a number of functions for which FTK Imager is not optimal. For example, a drive mounted as a drive letter with FTK Imager will not give you access to volume shadow copies. So that's one example where you might want to use a different tool to mount images. Things like running antivirus checks against an evidence file that so that you can see what existed on the system. Is there anything that we have to worry about or consider in our examination? And of course, yes.
Sorry, it's Carol again. Two questions came in. One asks, why use two virtual OSs to boot the target OS?
Well, we use a Linux distribution VM in the class to mount the E01 simply because we're using Xmount for the mounting, and Xmount is a Linux tool. There, you can do this. We've had success in our lab using VirtualBox in a Windows system. However, VirtualBox doesn't come without its bugs, and we've just found in a teaching environment that VirtualBox might not be the most streamlined tool for the purpose. So in normal circumstances, you might not do it this way. However, within the VM, it's contained, and we have to have a way to teach it in the class. So that VM exists in order for us to be able to teach it in the class. Was there
All
another
right, thank
question?
you. Yeah, the second one was this VMDK file is running in read-only mode or read-write mode, they're questioning. Rebooting this virtual OS will reset our activities done, or changes will remain in VMDK? Question mark.
The changes should remain in VMDK. It's when you boot up the E01, it's creating a cache file to keep track of all of the activities you're doing so that it's not affecting the evidence file. And the cache file persists, and then the VMDK does exactly what the VMDK does in any environment, in any VM environment. So yes, if I was to run a search in the browser that I had open, and then I rebooted this system, that search history would persist.
All right, great. I'll let you get back to the slides. Thank you.
Okay, so then we talk about triage, imaging, triaging, grabbing the data that makes the most sense to us, that will help us move the ball very, very quickly. And it's easy to talk about triage imaging when you're at a party on a Friday night, because that's what we all talk about at parties on Friday, at least the parties I go to. Anyway, but what do we really know about that? Where does this evidence exist? Well, if you start to think about it, you think, well, browser history is of pretty immediate importance in many cases. Prefetch showing evidence of execution, the registry, which shows evidence of everything, jump lists, email link files, things like this, where the user's activity up to the minute is existing. But when we start to think about where does this stuff come from, then the conversation gets a little quieter, because it's easy to say, I want this and this and this. It's a different story to list off all of the locations where you would find evidence of the things we just talked about. And so wouldn't it be great if we had a cool list of all of these things? And up until now, we had the SANS posters that students would receive in their classes, which were indispensable for showing all of the different locations where this forensic artifacts live. And then, of course, Eric Zimmerman, being Eric Zimmerman, decided he was going to write yet another tool. And so he wrote the CAPE tool. Now, the CAPE tool, there's no single discussion, there's no single definition for the CAPE tool. The best way I would define CAPE is that it is the closest thing that the industry has ever seen to a forensic magic button, a forensic get me the evidence button. We've joked for years about how potentially less than optimal forensicators or examinations would just mount the evidence in the Gorilla forensic suite of choice and press buttons, and whatever the buttons couldn't get us, well, it must not be available. And we would always joke about the magic button. CAPE is truly that magic button. Now, Eric likes to say that CAPE doesn't actually do anything by itself. It has to have user input. So essentially how it will work is we can take an E01, or we could mount a live drive write blocked and perform these same functions. We can use F-response to reach out into the network and do the same thing. And the really cool thing, well, one of the many, many cool things about CAPE is that it will reach into volume shadow copies, as many as there are, and pull that same data out of the volume shadow copies. It pulls it out, it collects it, it will create it in a VHD, VHDX, zip file, a number of different containers. It's forensically sound, and it maintains metadata, which is very cool. And then we can run processing against it so that we can extract that data into some kind of a usable format. So why don't we have a quick look at CAPE, because let's face it, everywhere I go, it's always Cape this, Cape that. Everybody's got a million questions about Cape, and everybody wants to see it work. So, and I don't blame you. It is truly a phenomenal tool, and for the princely sum of free, which is pretty much the way Eric Zimmerman works. I don't know too many people who have contributed so much to the industry as Eric Zimmerman. So we would mount our image as a drive letter, which we've already done, and then Cape is fairly simple in its construct as far as components. This is pretty much everything inside the Cape folder, and once you mount it at the command line, you can point it at this folder and run the get Cape update function, and it will automatically update Cape. And then you can also update the targets and modules. When you run the update, it walks you through updating all of this. Let's have a look at some of the ways that Cape works. So Cape works off of the idea of targets and modules. So the targets, basically, what do I want to grab? What evidence do I want? And we've got quite a list of things, quite a list. Right now there's 52 of these, and really one of the great things about this is they're easy enough for anybody to write themselves. And to give you an idea, what you're looking at is the latest version of Cape. And just even a month ago, I just want to show you what it looked like just even a month ago. When we open up the target files here, we had 25 different things that we could reach out into our data to collect. So we want to collect Skype data, SRUM data, thumb cache, recycled bin, Outlook data, link files, jump lists. These were all in the list. Fast forward to today, we have 52 items. Why so many? Because they're easy enough to look at and edit ourselves. So for example, we can open up a target file, and this is the construct. It's done in YAML, so for its simplicity, and it's easy enough to just copy paste one of these target files and adjust it in any way that you'd like. Now you can see we're after, in this case, link files, and where do they live? We have the path to where they live so that the program knows where to go to get this information. Now, these are kind of the core files that Eric wrote, but it's so easy to write your own that a lot of these newer targets have been written by other people. So for example, this iTunes backup, a fellow named Tony Knutson created this target file, and he said, okay, I want to reach out to where the iPhone's backups live, and I want to pull them out. Now, the target file, that's what the target file's job is to pull, to go in and find the files that exist and grab them and put them somewhere. Why do we want to do that? So that we can then run modules against it. So in this modules folder, you see a number of different functions that we can perform. Now, I showed you the iTunes backup target collector a moment ago. So I'm going to look at this iTunes backup module. The module actually runs the functionality against the collected file. So in this case, a gentleman by the name of Jack Farley created a module. What's a module? A module is merely a file that runs an instruction that goes into the file we collected, the target file, and suck out all the data and present it to us in a way that makes sense, that's actionable for us. So in this case, it's leveraging iTunes Backup Analyzer to look at the backup that we created or that we extracted and parse it out. So when you run this, when we run Cape, I'm just going to navigate over to my desktop. Oh, should go on deeper. We're in the Cape folder. So now I'm going to, let's say that you decided that you wanted to create your own target files. How do you know that it's correct? How do you know that it's going to work? Well, Eric anticipated that. So once you create a target file, it's just as simple as navigating to the CAPE directory, starting the CAPE software, and then just running a target list against it. And it will look at all of the targets that have been created to see, do they all work? So you can see in this case, outside of the 2 disabled ones, all of these targets excuse me, came through just fine. And if there was any mistakes in them, any syntax errors or things like that, you would get a message back saying that something needed to be fixed. So that's the command line. And due to some urging by, I think it started with O.V. Carroll actually, Eric decided to create a GUI version of CAPE for people who aren't command line inclined. So this is GCAPE. Now in GCAPE, we can do something like we want to use target options, obviously. We want to go grab our data. So we're going to point it at the mounted drive that we've mounted. Now that can, in this case, we're actually using a triaged image already, but you can point it at any drive letter. And then where do you want it where do you want the data, the collected data to go? Well, in our case, I like to create a folder called cape_t for targets. And then you see this flush button. This flush is critical. I'm not going to go through every feature of the program just because of time constraints, but the flush program is pretty important and a source of contention for some users and certainly for Eric when people don't realize what it's for. Flush is exactly what it sounds like. It is going to flush the contents of that folder to empty it out. So you have to create a directory that you don't mind being cleared out. If you decide to make your target destination the desktop, well, guess what happens when the flush runs? Everything on your desktop just got flushed. So that's the flush command. You can turn that off, but I don't recommend it. So I'm going to point it at this folder, this cape_t folder that I created. And then I'm going to go through here and I'm just going to pick some of the stuff that I want to grab for stuff that we're going to analyze. So I'm just going to grab evidence of execution. I'm only going to grab a few of them here. I want link files. I'll grab recycle bin stuff. I'll grab the registry hives, and I'm going to grab USB. So I've decided those are the targets that I want. That's the information that I want right now. And I don't just want it from my system, but I want it from all my volume shadow copies. Anybody who's worked with volume shadow copies knows how problematic it can be to pull volume shadow copies. Well, all you do to grab them here is click a button that says process VSCs. And then you can deduplicate, so you're not looking at a whole bunch of crazy noise. You can pick your output. Where do you want the targets? How do you want the targets presented? I'm just going to leave it as none. And because I'm lazy and because I don't want to have to do, the heavy lifting, I'll let CAPE do that. Not only am I going to pull the evidence that the files that hold the evidence I want, I'm also going to run functions against them as soon as they're pulled. So in order to do that, I'm going to point it at that the target folder that I created, where all of the files are going to go once I pull the targets. And then where do I want them to output to? Well, I'm going to put them in a cape-m or module folder. Again, I want to run the flush command because I don't want to commingle data. And then I have to tell it what do I want to run against the files that I collected. So for example, I pulled my registry, so I want to see auto runs. And let's grab jump lists and link files. Now you may think to yourself, Kevin, we've only got an hour here and you're pulling all of these files. This is going to take forever. Well, prepare to be disappointed because it certainly is not going to take forever. So I'm going to grab my shell bags, love the shell bags, and I'm going to grab USB stuff. Again, I can decide how to output them, but I'm going to leave it as default. Now, all of the stuff that I've selected, you see down in the current command line, this is basically, I could, if I was at the command line and I typed this, it would give me the same output as the selections I've just made. It's simple as clicking execute. You're going to get a warning about flushing. Hey, you're about to destroy everything in those folders. That's okay. Now, the downside to using CAPE is that not only am I going in and collecting everything that I think holds the evidence I want, but I'm also parsing it and outputting it to something that makes sense to me. The problem is I don't have time to go and warm up my coffee because we're done. We're done inside of probably 30 seconds, 26 seconds. And it's done. We're ready to forensicate now. What do we look at? So let's go back and see what happened. This was our target folder. We told CAPE to go in and grab our stuff. So it grabbed all the recycle bins and basically all of the data that we wanted to grab, that we told it to grab. You can also see all of that exists inside the volume shadow copies as well. And then let's go look at what happened. Well, we told it we wanted to see the recycle bin. And by the way, if anybody's ever worked with any of the viewers that Microsoft has created, you've probably had less than a stellar experience. Well, while we were actually sitting together working on this class, I made that very comment. And Eric said, challenge accepted. So inside of 10 minutes, he wrote a program called Easy Viewer, and it's part of our VM. And Easy Viewer, if you don't have Office on your system, will allow you to mount just about any file. And the cool thing is, it also allows for the sizing of columns, which the Microsoft Viewer doesn't do. So we get to see the file name, delete it on, and we haven't had to do anything. CAPE did all of the heavy lifting. What else can we see? Program execution. We have all of the prefetch output. We can, again, open that in Easy Viewer. And we get to see prefetch data. And it's truly as easy as that. We've got our run counts, last runs, and then any dates and times that might be available to us, the volumes they've run from, et cetera, et cetera. Now, any of you who've been doing this the old way know what a time saver this is. And you can take all of these and put them into, well, yet another Eric Zimmerman tool called Timeline Explorer. You dump all of these into Timeline Explorer and you can slice, dice, and sort these in any way you want to get at the data as quickly as possible. Then we get into data acquisition, which is the other half of the class. We talk about dead box acquisition just to cover it because, you know, there are people in the class that have never done that before. So we show it. Then we talk about live acquisitions and preparing destination media. How do I sort out the destination media? Do I have to wipe my destination drives? This is stuff that people are told for years because that's the way we used to do it. Well, we explain why you used to have to do it and why maybe it's not quite so important today. We get into things like media removal. How do we get at the hard drives or the storage devices in the computers of today, the laptops, the desktops, various different pieces of equipment? We talk about specialty media, SANs, large storage arrays, NAS devices. We talk about devices that you can't remove storage from. So things like a Surface Pro, in some cases that have one port. Well, how do we plug in everything we need to plug in for an acquisition when we've only got one port? So we go through that. And by the way, I might add that we also have quite a number of studio quality videos that were shot in a professional recording studio to show step by step the acquisition processes and various different processes that I've been outlining and that are in the course. and you get all of these high quality videos, because some of these things we can't do in class. As much as I'd like to be able to give everybody a Surface Pro, Sam's kind of shot me down on that, said that it'd drive the price just a little too high. So we videoed it instead, and very, very high quality videos. We get into multi-disc storage, various different styles of RAID, RAID 0, 1, 5, 6, just the common ones, nested RAID 10, JBOD, just a bunch of disks. We talk about live acquisition. What can we do with this? How do I explain if my hashes don't match? What about write blocking? Will this change the data? Will the court take my evidence? Why can't I just turn it off? We address all of these questions that come up time and time and again. Then we talk about remote acquisition. We get into network acquisitions, cloud storage, getting into Office 365, Google Takeout. If you've never heard of that, I suggest you Google it. And then, of course, we have a whole bunch of love for Apple. The problem with Apple is it's an entirely different approach. We have to concern ourselves with the physical format. We can't take the hard drives out anymore. How is the data stored? What about encryption? What about file systems? So we have to approach those entirely differently, with different boot disks. What do we do about live imaging and APFS, core storage? How is file vault affected? Is stuff encrypted from the factory now or not? And then we talk about the dreaded T2 chip and how we can, I don't know, get around it is kind of a bad word because you don't get around T2, but we talk about the T2 chip and how that's going to affect our imaging process and the data that we collect. We get into a section about a little bit about internet history and the construct of domain names and numbers from the beginning of time, and we talk about the mushroom that nearly took down the internet. I'm not going to give that away. This is top secret. You got to come to the class to learn about the mushroom that just about killed the internet. We talk about network traffic and Internet of Things. Where's all of the traffic coming from? Where's it going to? How do we collect it? And nowadays with Internet of Things, this is a very real concern because so much stuff is happening on the wire. So how are we going to collect that data that's going back and forth on the wire? We show various methods to do that, pushing pretty much all of the captures out to a packet capture file. And then we put that packet capture file into various programs and we parse out the different types of data. We show how to filter and how we can really drill down to what it is that we need so that we can get the data. And a nice big picture disappeared off of this slide, which was really cool. So we'll just move right on. Now, what about the last esoteric stuff that I talked about? We talk about data carving. And data carving is not new to anybody. But what data carving needs pretty much is either intact files in MFT or at the very least an intact header of a file. Well, then we get into data rebuilding, which is what happens if you don't have either of those. Then how do you find what you need and how do you get at it? So let's have a look at data carving. We talk about data carving and we see on the right hand side a pull from a hex editor. In this portion of the class, we spend a fair bit of time in hex editors identifying structure and sweeping files out and rebuilding them. In the data rebuilding portion, we're looking in this particular case at a PDF. And what happens when the front end of the PDF is all stomped on and it doesn't exist anymore? But we find a hit maybe in a file path in the PDF. How do we carve that out and make it work again so that we can extract the evidence? That's kind of the stuff and we do that. We rebuild some pictures, we rebuild a doc and Docx. If you've ever done a data carve, say on Word docs, for example, you know full well that you've gotten to a folder and you have hundreds, if not thousands of files in there, and many of them don't work. You double click on them, you get an error message. So you say, oh, there's nothing there, and you delete it, and you move on to the next one. This class is going to show you what you've been throwing away, how in fact the data is in there and you threw it away just because it wouldn't open properly. So we show how to fix these files so that you can get at the data. Then we get into data recovery, and we don't spend a whole lot of time in here, but this is mostly just some ideas of data recovery. We dispel a lot of myths. We talk about what data recovery is and isn't, what we can get, what we can't get. And then we look at two problems that happen on drives, things like when the heads get stuck on the platter and when a transient voltage suppressor gets baked. Two problems that you can fix yourself if you're not going to send it to a lab. We don't recommend it, but if you know you're not going to send it to a lab anyway, then we've got videos and techniques and demonstrations to show how a lot of that stuff can be done. We also have a data recovery lab where we point a data recovery tool at a evidence file we've collected where the MFT has been completely destroyed, and we still pull data off of the drive and get the structure back. I know that's a whole lot of data in a very short period of time, but that's training by fire hose, and that's SANS mantra. So I'm available for any questions.
All right, well, thanks. At this moment, we don't have any new questions. We answered the ones that had previously come in. Oh, someone just wanted to say that he's excited to get into this class.
We're excited to have you, whoever you are. And the next run is Beta 2 in Austin, Texas at the D1 Summit. Unfortunately, that is entirely sold out. But we do have a class I think, coming up in New Orleans and another one in Orlando towards the end of the year. Just keep a look at the SANS page and follow us on Twitter, and you'll find out when these are all running.
All right, someone says you've sold me. Thanks, Kevin. Someone has a question. There's going to be a possible R45 tour.
Obviously a Rush fan. You're going to have to come to the class to figure out why that's there.